page table to handle segments, right? The page table is kind of straightforward, simple, I understood it. But segments are a little bit different because for one thing, they have a length. And they're all different lengths. Page tables, I didn't care about the length because they were all the same length. But that's not true here. I'm going to be concerned with knowing the length of my segment. Yeah, I need to know if it's loaded. And need to know if it's been written to. All those kinds, those things are going to be the same. So our virtual address is going to be similar to the page table's address, where we're going to have, in this case, the segment number and the offset. So we'll still have the same two parts to it. But our segment table entry now is going to have the base address for this segment, where it gets loaded into main memory. It's going to have its length, it'll have those control bits, and it'll have its modified bit. Okay? We're also now going to be concerned with this bit, the present bit. Is it loaded in main memory? So our address translation from logical to physical will look like this. If I reserve 4 bits, this is a 16-bit address just because the math is easy. If I reserve the first 4 bits for the segment number, right, then I would go to the process segment table, I would then find the length and base address for that entry inside the segment table. In this case, address 1, so I want, right? And then I have my offset. So I would do the same thing here where I would go and get the base address for it with the offset to generate this. The length is now going to have to be managed by the operating system when it's moving segments in and out of main memory. It's also going to be concerned with memory addresses being formed during runtime, because we now have to be concerned with references of memory outside of that segment. We do in pages as well, but we can do it outside of the addressing scheme because all pages, all frames are equal sized. So we'll come back to that a little bit later. But for the case of segments, I'm now going to have to be worried about that here in my segment table. Okay, so what this is saying is that you got a partition somewhere, paging schemes, equal sizes pages, and you've got your relative addressing, gets you to a specific address, but in the segments, what you're going to do is you're going to create memory and load it based upon the size and length of that particular segment. So from address 0 of segment 1 to its total size will be assigned to that particular segment's memory addressing, legal addressing scheme. So you can see it's a little bit more complex. And we're going to have to build more error checking into that as a result. The other thing to be concerned with is that of segmentation in this case, fragmentation in this particular case here. In the case of segments, what's happening over time is a segment's going to get loaded, and unfortunately this example only shows 2 segments. But segments are going to be loaded, and they're going to go away, they're going to get swapped out, other segments are going to get called in. The problem is, as segments come and go, you're going to introduce fragmentation within the main memory itself, because you're going to create holes, because the next segment coming in is going to be a different size. Or I might, instead of having a single segment here, I might get 3 segments here. And then maybe the middle segment goes away, and somebody else comes in and wants a different segment. Well, every time you go to load a segment, you're going to be concerned with, do I have enough consecutive addresses available to load that particular segment into that available memory location? Remember, we had this concept, we had this mechanism in our paging system where we actually had a page table for the free list, right? Remember that? Great test question. And that's an easy way for us to determine if there's a page available, a frame available, so we can load our page in that frame. In the segment list, that's not so easy to do, because, yeah, I can have an available memory address, what's its length? Okay, so for this one in the middle, like I said, if I have 3 in here and the middle one decides to go away, the one in the middle, when I free it up, I'm gonna have a starting address, and I'm gonna have its length, or maybe a starting address and ending address. Then I'm concerned with what's at the next address. Is that free memory as well, or is that a loaded segment? If it's a loaded segment, that's fine. I can then go ahead and manage that free space. But if it's consecutive, what I would want to do is go ahead and grow this empty segment into a larger empty segment. All right, so if this middle one was freed up, but oh, by the way, this one after it was also freed up, I'd want to make that one big free address space. So if I have a process coming in, wanting a large space, I would have it. So freeing up memory is a little more complex now, right? Because I'm always going to want to check the neighboring address to see if it's free or not. Does that make sense? Questions? Okay, so I'm going to be creating these holes or segments inside of main memory as processes release their segments. And I'm going to have to manage them. We can see this is going to get pretty complex pretty quickly, isn't it? Yeah, we have the efficiencies we talked about before the break, but now I've got this complexity about managing the free space. I also have the complexity now of finding free space. Anytime I want to move a segment, do I grab the first free space? What if it's a small segment? The first free space happens to be a very large one, but I've got some smaller ones later on down here. When I want to use one of those, yeah, because then I have a better chance of another process needing a large segment to take the large one into build. So if I want to do any kind of optimization, I've got a lot of conditionality to deal with. And with the number of page faults that we're generating in the page system, if you equate that to segments, which are even more, that's a lot of overhead work. It's going to get pretty complex pretty fast. So it's a great concept. We like the idea of allowing the memory being managed by the memory the process really needs. But to implement it is going to take a lot of extra overhead. Perhaps that's not the best approach. Well, let's not totally throw it out, because there's some good ideas there for gaining efficiency, particularly if we go back to our page systems. And we recall that we always know the last page is going to be inefficient. And half the time, it's really inefficient. So, is there a way to take some of the things we're doing here and combining that with the efficiencies we get from paging? And that's what a lot of good research went into, and that's what a lot of systems are doing today. They're doing this combined paging segmentation memory system to generate the virtual addresses to try to best optimize the use of those pages. So here's what works. Again, we want all this to be transparent to the program. Poor programmers got their hands full just trying to build the functions, right? Not to worry about system stuff. We want to eliminate external fragmentation. We want to optimize the use of all pages. We also want to optimize runtime of our faults. Okay, and so to do this, what we're going to do is have the compiler still do the same type of work it was doing with segments. But since compilers run once, right, your executable is running a whole bunch of times as processes over and over and over again. So if we allow the compiler, when it runs once, to determine how to map these different sizes of segments into pages so that it can optimize the best use of all the pages it needs. In other words, the best fit, right? Because I'm still going to have the same problem. I've got all these segments of different sizes, but I still have fixed memory blocks, my page size. So there's still going to be some inefficiencies, and it may now be a little bit of inefficiency in each page, but I'm not going to have this huge inefficiency on the last page. But the compiler, running once at compile time, can do this optimization for fitting these different segments into the smallest number of pages as possible and using as much of each page as possible. That's what we're going to talk about. So if we can do that, what would our virtual address look like? Okay. Well, we saw what the page table virtual address looked like. We saw what the segmentation table looks like. This is what a combined scheme would look like. Okay? Virtual address, we would have a segment number, then we would have the page number, then we would have the offset within there. The segment table entry then would have the length and the segment base because we are still concerned with those two things. And then the page table would simply need the frame number and the modified bit and the present bit. Let's don't worry about that present bit. Then to form the virtual address into a physical address, we would do the following. We would take the segment number. We have the segment table pointer in a register somewhere, which would then get us to the start of the segment table. Segment number is a relative entry inside the segment table. And then from here, we would work with the page table, which we would have the page number, which would be a relative entry inside the page table. Ooh, that's not even a relative number, it's because we're always started here. So it goes straight to the head of the page table, and a relative address within the page table. To look up, to generate, because it would have that value of the page frame number now in here, to put inside of there, the offset would go there, generating a physical address over here. Okay, so no additional work, but we are dividing our addressing bits up into 3 components now instead of 2 components. And since the hardware is doing this in a single instruction cycle, there's nothing lost from an efficiency standpoint. We do have a little bit more complex table now, so it is a little bit larger, but it allows us to reduce the external fragmentation and optimize the use of every page. Questions? Sure. We covered a lot of material. Before we go any further, just kind of review what we've done. We've looked at our virtual addressing schemes, which consisted of logical addresses. We talked about the relative addresses. We talked about the physical addresses. We talked about how to generate a virtual memory address, how to translate that to physical addresses. We talked about the different hardware components that are needed and to optimize it, including the TLB and cache memory. And what else did we talk about? Oh yes, the pluses and minuses of pages versus segments, and the combined technique and the pros and cons of each of these different methods, right? Got it, right? The reading, right? The readings. It's all about the readings. And going back and seeing if you can reproduce what we've covered here, right? That's the only way you'll really know if you understand this, is if you try to explain it to somebody. Somebody could even be somebody not in this class. Somebody could be a friend, dog, cat, right? If you could explain it, yeah, some of you have heard this before. So if you could explain this, then you understand it. If you can't explain it, then that means as part of it, you follow the logic as we discussed it here, but you don't understand it enough that you can explain it to somebody else. Okay? If you can explain it to somebody else, you understand the material. Okay? So having said that, and being concerned that you really didn't capture maybe 60% of what we covered, I think this is probably a good breaking point. Because I know you're still over there saying, I want my exam back. I'm still thinking about that exam. I don't understand my score. And this is where we want to break in, because this is what we're going to go over on Thursday night. Okay? Wednesday night.